So students, good morning. Today I am continue with the same topic which where I left yesterday. Yesterday I showed you how to design a FIR filter. Now today I will start with the filter design using window sequence. Window means I will focus on certain areas. That is the pass band and the transition band. Maybe stop band up to a certain extent, because if you see, as you have studied, there are a lot of oscillations both in the pass band, in the stop band, and the transition period between the pass band and the stop band sometimes gets the quite large. So the purpose of digital filters using FIR filter type design is to reduce the oscillation both in the pass band and in the stop band, and also to reduce the transition band time period. So there are various types of filter design techniques using various types of windows, like the rectangular window. From the name you can identify that the shape of the window is rectangular. Then there is triangular window. More specific windows, the more specific windows are the Hanning window, the Hamming window. Hanning window and Hamming window is very important. This one and this one is very important for semester exam. And also there are other window techniques like Blackman and Kaiser. So mainly I will focus on Hanning and Hamming window technique. So as you see, for rectangular window, the window coefficient is always 1. What is window coefficient? How do we calculate? I'll get into that when I come into the problem. For triangular window, the window coefficient can be calculated in this manner, where capital N is the total number of samples and the small n is the individual position, that is 0, 1, 2, 3 and something like that. This is equal to given by this formula if the samples are taken in this manner. I can take it in this manner, I can take it in this manner, and if I take it in this manner, the window coefficient has to be calculated for triangular window using this expression. This you will have to remember. The window coefficient, how it is being calculated using Hanning window technique, is this one. If the samples are taken in this way, that is from n minus 1 by 2 to n plus n minus 1 by 2, and it is 0 to a, and it is this one if it is from 0 to n minus 1. Similarly, for Hamming window, the window coefficients has to be calculated like this. Hanning and Hamming are very important for exam purpose. Then we have the Blackman window and the Kaiser window. The window coefficient techniques are calculated in this manner for 0 to n minus 1, and from minus n minus 1 by 2 to plus n minus 1 by 2 by using this expression. The similar thing is for Kaiser window. Now let me get to a problem. Design a FIR filter having filter specification, this one. From the specification you can understand that this is nothing but a low pass filter, and using Hamming window technique with the total number of samples to be 7. So the filter technique is given, so the filter specification is given with this one. So like yesterday I have done with inverse Fourier transform to get the response in the time domain. The integration continues, and this is what I get, the impulse response for n is not equal to 3, because if I put here n is equal to 3, this factor becomes 0, means it becomes a discontinuous function. So here for n is equal to 3, I will have to apply the L'Hospital's rule. Using L'Hospital's rule, I get Hn3 is equal to 0.25. The other filters coefficients can be calculated in this manner by putting n is equal to 0, 1, 2, 4, 1, 2, 4, 5 and 6, because 7 samples, so 0 to 6 are the total number of samples. So the filter coefficients are now we have got. Now using the Hamming window technique, this is the formula for to calculate the window coefficient, because the samples I have taken is between 0 to n minus 1. Here you see I have calculated between 0 to 6. 0 I have started and I have ended at 6. Means 0 to n minus 1, this is where I have computed the window parameters, the impulse parameters. So I have used this one as the window coefficient, this formula. Similarly, I have calculated the window coefficients just by using the formula, this one. For 0 it is 0. I have got the results. So what is the linear coefficient finally? The impulse response, that is H0 is equal to this, what I have got, multiplied by the window coefficient, the results. So what it is actually, the impulse response without window coefficient multiplied by the window coefficient is the final impulse response using window coefficient technique. And this is how I get the compute the frequency response, and finally the transfer function of the digital low pass filter just by using the formula I have computed. Just to give you one more example, suppose I want to design a linear high pass filter. If I have having cut off frequency, this one with 7 samples, so the frequency response is given by this one. Again the computation continues. So this is the result which I get for all n except for n is equal to alpha, because if I put n is equal to alpha, this factor becomes 0 and it becomes a non discontinuous function. So I have computed again. I have computed. I have since I am taking the sample from 0 to n minus 1 using Hamming window, I have used this expression. So the impulse response are being computed for other parameters, as you can see. For 0, 1, 2, 3, 4, 5, 6, these are being computed. And finally the transfer function of the FIR filter is given. It can be computed in this manner just by using this formula. N is equal to 0 to 6 Hn z to the power minus n, the normal z transform equation. So this is what for today. Tomorrow I'll again come back with some notes on FIR filter. Thank you.